Welcome to the 34th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to talk about the research that goes behind the book itself. This project inspired many dozens of research projects. Each of them were completed in the course of writing the book itself. And in this video, I'm going to discuss both the ones that appear in the book and a number of other ones that are related and inspired by the project. I certainly never would have engaged in them had I not been involved in this project. But for one reason or another, they don't quite fit into the book, either because they're using calculus or complex analysis as part of the tools that are being used. And in this book, I tried very hard to keep everything at the more elementary level in terms of the math. But I thought it would be interesting to tell you about them anyway. And one of the things you will find along the way is that much of this work was done with citizen scientists, with high school students, and with undergraduates. And they were fantastic colleagues to work with. I learned a lot from them in the process of going through these projects. And I want to illustrate this to really point out that you who are watching can also become a researcher. It just takes effort, and the final video that I have will contain some thoughts that I have about how you can get involved in doing research yourself. So the first project we were involved in involved working with this wonderful former engineer, Bill Courtney, who's pictured there on the left. In the first running of the Quantum MOOC, I would get these wonderful forum discussions from Bill talking about details in logic, places where maybe my logic was a little bit weak, or where he had some interesting thoughts about how things could be discussed or how things could be detailed. And I just learned a ton from these conversations with Bill. I bet if you talked with Bill, he would say, I don't know what you're talking about. I don't think you could have learned anything from me. But Bill, I actually did learn quite a bit from you. And in the process of our discussions, I decided it would be very interesting to take the classic Stern-Gerlach experiment, which is used at the introduction to quantum mechanics in any textbook that is doing what is called a spins first format, and we could rework it to talk about delayed choice experiments by working with an internal degree of freedom in the atom. And I had to bring in Paul Julian, who is an expert in atomic physics, to help us understand exactly how one might be able to carry out these kinds of experiments using atoms. And Lucas, who was involved in creating the tutorials, was key in helping us get the illustrations for this work as well. Next up is one of the favorite things that I did during this project, which was figuring out how to calculate spherical harmonics without using calculus. One of the things that I think I really hated about the traditional way of doing quantum mechanics was how much I felt that determining spherical harmonics was extremely tedious. I never felt like I could do the steps that I was told to do. And in the end, we usually didn't actually go through every single step and get to solving for what the associated Legendre polynomials were. Instead, at the end, we were just told, here's the differential equation and these are the solutions. And I really was dissatisfied with that. And when we figured out the right way to do it without derivatives, I began to have a clear physical understanding of exactly how this worked. And on this project, I worked with Mark Weitzman. Mark Weitzman has a web presence. Many of you may actually know him. He is a former professional poker player. He first started off as a lawyer. He went to Caltech and got a master's degree in physics, and then went off and became a professional poker player. But he's always loved physics, and he's always been involved in it. He does a lot of MOOCs. I met him through doing MOOCs myself during the MOOC craze, and it was a lot of fun to interact with him and work with him on this project. One of the next ones we had was looking at solving the particle in a box with these operator methods. The particle in an infinite square well was solved by Schrodinger. He called it shooting sparrows with artillery. Here we were looking at particle in finite square wells, and that doesn't yield so easily to the factorization method. In fact, we didn't know it at the time, but the technique we were using is a technique that we now call single-shot factorization method. And this project helped us understand how to do it. I worked with two wonderful high school students, Alex Jacoby and Maurice Curran, and I also worked with a physics professor, David Wolf, who was at Austin Community College. He was someone who I also met in the MOOC space, and this paper was one where we used operator methods to solve the different particle in a boxes, and then we worked out a nice variational argument to show that in one dimension and in two dimension, those problems, any attractive potential always has at least one bound state. Now, of course, that's a result that is well known, but I really liked the way that we could formulate the variational argument, and that was why we put that into this paper as well. And it's the exact same variational argument that I use in the book. Next up, we were so successful with the MOOC, we wrote an article about it for the physics teacher, and this involved all the people who contributed to the MOOC. That included Dylan Cutler and Lucas Vieira Barbosa, and also Anna Cruz, who was someone from Georgetown in a department called CANDLES, which is the Center for New Designs in Learning and Technology, or I got something quite a little bit wrong because there's an S in there. But in any case, she was assigned to help us on developing the MOOC, and she provided a lot of interesting insight, and she also did with the paper that we wrote as well. Next up was one of the things that I also am fairly proud of, was figuring out how to algebraically determine the wave function of the simple harmonic oscillator. This is work that I did with Mike Rushka as part of his senior thesis. Mike was an undergraduate at Georgetown at the time, and we actually did this during his junior year. Another problem that I worked with a citizen scientist here, Thomas Szymanski, who is in Poland, was an algebraic derivation of the Kramers-Pasternak relations. The Kramers-Pasternak relations are ways in which you can calculate the expectation values of r to the n in any energy eigenstate of the hydrogen atom. They're typically worked out using rather complicated calculus arguments. In fact, most textbooks don't know about this, and they just tell you what the integrals are for powers of r in different energy eigenstates. And I wasn't so happy with that. I was thrilled to learn that there was a general way of doing it, and it took us quite a while to figure out one step that we needed to do using operators rather than using calculus, because the standard way of doing it is by using the Feynman-Hellman theorem, and using our operator method, we didn't want to use the Feynman-Hellman theorem. I think this is a very nice paper. It is technical. It is a little bit hard to get through, but it's very nice, and all of the material about it appears in the book. Next up, we had a project that I was involved with Anna Galler and Jeremy Canfield. Anna actually came out to visit Georgetown for 6 months, and she started a week before lockdown occurred during COVID. And she ended up staying in the Washington area for about 4 months, 3 or 4 months before she went back to Europe. This was a project that I had suggested to her because we didn't have enough time to do a completely new solid-state physics project, and I thought that this would be nice to help her career. Often when you're a young person trying to find work in physics, if you have pedagogical papers, you can help bolster the teaching side of your resume when you're looking for jobs. For Jeremy, this was one of his, I believe this was his first problem as a graduate student. I had already worked on some research with Jeremy as an undergraduate. He was both a Georgetown undergraduate and graduate student. And what we did was we revisited Schrodinger's original quantum mechanical solution for hydrogen. I did not know that every differential equation that has both constant coefficients and linear varying coefficients can be exactly solved. I knew that constant coefficients could, but with linear coefficients also can, and that method to solve it is called the Laplace method, and that's the method Schrodinger used to solve for the hydrogen wave functions in his first paper on quantum mechanics. It's kind of a lost art. We wanted to bring it back, let people know and understand exactly how that worked, and it was a lot of fun working out the details of that in the paper. This is stuff that does not appear in the book. Next, I had been working now for about a year, maybe 2 years, with both Wes and Mark in talking about lots of things related to factorization. Wes was the person who had introduced me to the factorization method. I had not heard of it before he had introduced it to me. And one of the things that we ended up getting involved in was that a technique that is needed when you're trying to calculate wave functions is to be able to work with the translation operator. But if you want to do this in spherical coordinates, you better have the translation operator in spherical coordinates. And to my shock, no one had ever worked this out. I couldn't believe that this had never happened. Turns out it's actually a pretty hard problem. There's lots of interesting stuff in it. This is stuff that's completely covered in the book. And it was the second paper that Mike Rushka was engaged in during his thesis. And Wes Matthews provided some incredible insight into a number of the technical aspects of the work. Really helped us figure out all the details for how to make it work. I think it's a very nice paper, and I hope you enjoyed the discussions about it in the book itself. Then I got an email from both Eduardo Munguia Gonzalez, I hope I'm pronouncing your name correctly, Eduardo, and Sheldon Rigo, who had been referred to me by Mark Weitzman. They had been taking the MIT online quantum mechanics course and they wanted to get engaged in research. And I very happily agreed. The problem that I decided we should work on was figuring out how to get the wave function of a squeezed coherent state. Very closely related to the harmonic oscillator ground state, but it has a lot of different technical details that go into it. And it turns out that, interestingly, if you look in many different quantum mechanics books, even quantum optics books that talk about squeeze states, you never see them writing down the wave function. I think I found it only in 1 or 2 quantum optics books out of the maybe dozen that I looked through. And so we thought this would be an interesting thing to show how you can do this and get the wave function just by working with operator methods. Then we got engaged in work. This was really work that was led by Wes Matthews. Mark Ezrick was involved with this, as was Zuyao Tiao. Zuyao was someone who I also had met through the MOOCs, and he was a math professor at the time in Malaysia, and he was interested in getting involved in doing some work in quantum mechanics. And what Wes discovered was something that I had probably had some hints about, but he really clearly showed exactly how this works. The hypergeometric and confluent hypergeometric differential equations are odd compared to most other differential equations that mathematicians study. These equations were the functions were first defined in terms of their power series, not the differential equation that they solve. Only later was the differential equation found that they solve, and as a result, they're not defined as the 2 linearly independent solutions of the differential equation. In fact, what happens is you vary parameters in the hypergeometric differential equation, you find the 2 solutions that are normally linearly independent become proportional to each other at certain special values of the parameters. And it turns out that nearly every quantum mechanics problem that we solve involves us using exactly those special parameters. So while it is very common when you're solving a second-order differential equation to just look at a linear combination of the 2 linearly independent solutions, that method fails at these special points. And you will not find a single quantum mechanics textbook that talks about that and describes the right way to do it. And Wes worked out all of the details for figuring out systematically how to do it. I think it's a very important paper, and you might be kind of shocked as what is it doing in condensed matter physics? Well, condensed matter physics is a Ukrainian journal. I have a lot of Ukrainian colleagues in science, and this paper came out shortly after the war started. I wanted to find a way to support Ukrainian science, and I knew that perhaps their journal might have fewer submissions during this period of time. And so I asked them whether or not they thought it would be a paper that they would be willing to consider, even though it wasn't really condensed matter physics. And they happily did, and I'm very glad that we were able to publish this paper in the Journal of Condensed Matter Physics. Next up was trying to find a new way to solve hydrogen. We do this without angular momentum using the Cartesian factorization. Now, the Cartesian factorization was worked out, I think, in 1984 by a number of Russian scientists, including a famous one, Larkin, I think. Yaffe or Larkin? Now I can't remember exactly who it was. That's one of the things that happens when you get old. You start forgetting some details about people's names. For me, that's the first thing that seems to go. Bruce Liu, who is on the left, was another person who I met through the MOOC space. He was a civil engineer, but he wanted to get into physics and get into a physics PhD program. I had told him one of the best ways to do that is by getting involved in research, so you can show that you can actually do research, and he was very instrumental in this work. Christina Daniel was a graduate student at Georgetown who also contributed some important parts to this work, and this project was a really tough one. The technical aspects of it were super hard. There were a lot of times where we got stuck, and then one of the three of us would say something or figure out something that eventually would get us unstuck. And it took us many years to solve this problem. But the final result is really quite neat. It is a direct way of getting the wave function in both position and momentum space, and it's the only way I know of that you can get it in a simple way directly in momentum space, although there is a separate technique that can be used, but it involves doing some things that are a little bit more advanced in order to be able to get the wave functions this way. It was a really neat project. I really enjoyed working on it, and it really tested the boundaries of what we know about factorization and working with operators. Here's a pure research paper that I was engaged in. I have been involved in doing some work in quantum chemistry, primarily doing quantum chemistry on quantum computers. And one of the things that came up in that field is that the traditional way that you do quantum chemistry on conventional computers is using the coupled cluster approach. But on a quantum computer, you have to use the unitary coupled cluster approach. And while coupled cluster was developed in the 1960s and unitary coupled cluster in the 1990s, no one in chemistry really understood the relationship between the two and how you could write a quantum state as a coupled cluster ansatz versus how you could write it as a unitary coupled cluster ansatz. And it turned out the key to this was the exponential disentangling theorem, which most chemists have never heard or seen of. But once you apply that to the problem, it becomes really simple to relate the two. And this is something that became a chapter in the book, and so I wanted to share this paper as well as one of the research projects. Then Anna and Jeremy and I worked on applying the Laplace method not just to the hydrogen problem, but to all problems that can be solved with confluent hypergeometric functions. It turns out the Laplace method solves all of those problems. There also are problems that can be solved with the hypergeometric function, and the Laplace method is not sufficient to solve that. And I believe it hasn't really been worked out exactly how you create the general solutions of both hypergeometric differential equations and the more complicated cousin called the Hund differential equation. So this is actually moving into things that are full-blown research problems that no one knows about. But we satisfied ourselves just working with a confluent hypergeometric function where everything is well-defined and known. And again, this is a very nice set of work that we did. We were able to work out both the bound states and the continuum solutions for these different cases. Then I took work that Wes Matthews had completed, but he had not yet published it before his untimely death. He passed away while we were working on a project to try to find a different operator way of finding the hydrogen atom wave functions in momentum space. And it really came out of the blue without any warning. He was elderly, but he was in incredible shape, much better shape than I was. I frankly thought he was going to live to 100 at least, but unfortunately he did pass away. This is actually an image from one of the last Zoom videos that we had together. We would meet every Friday for a Zoom meeting, and I really wanted to make sure that I could honor his work by getting that work out and published. And so this is one of those articles on things that he had worked on finding continuum energy eigenstates using what we call single-shot factorization method. So this is the first paper that really is a follow-up to that particle in a box paper where we really sorted out how to do single-shot factorization. Then I decided in a conference that I was attending in Prague, which is a non-equilibrium many-body physics conference, to give a talk about how you measure the momentum of single quanta and write a conference publication on it. And this was something that was really kind of intriguing. I had a lot of people at the conference really interested in my talk. I'd given talks at this conference, I don't know, 10 times before, and yeah, there were people who I knew who said, yeah, I'll come attend your talk and so forth. Never did I have so many people so excited to see my talk, so it was fun. People are really interested in these fundamental topics, and I really think it's a shame that most quantum textbooks and most quantum classes don't actually teach you how you measure the momentum of a single quanta, and yet they still want to tell you that Heisenberg's uncertainty principle says you can't measure position and momentum at the same time. I don't think it's fair to say that if you don't tell us how you measure momentum, and then you learn that that statement isn't true. You actually measure position in order to measure momentum in most cases. Then next up was a follow-up to the squeeze state wave functions, where we looked at the free expansion of a Gaussian wave packet. This is a very classic problem in quantum mechanics, but we did it using operator manipulations, recognizing that it actually was a squeeze state problem. Now, we weren't the first to recognize that it was a squeeze state problem. A number of people had done that previously, but we were the first people who actually worked through all the details of showing how that works using operators as opposed to differential equations. Then I got involved in another conference proceeding, and this time it was work with Leanne Dowdy, who is a physics education researcher at Georgetown, where we discussed the issues of when you try to make quantum mechanics accessible and take out the differential equations, you still have to deal with the fact that students have to become comfortable working with abstraction. And this is a challenge because sometimes people have trouble getting into more abstract ideas. So we talk in this paper about some of the strategies you can use to ease them into abstraction. And it's the same strategy that I use in the book, starting first with the conceptual ideas, then slowly developing the formalism, and then eventually getting into the more abstract ideas. Then I went to another conference in Europe and presented a paper about explaining why, if you want to bring quantum mechanics education into the high school, which I think would be a great thing to do, it's really important for the teachers to understand the concepts and conceptual ideas of quantum mechanics, which they almost certainly were not taught. And the first 4 chapters of my book are really the materials that help you understand conceptual ideas and conceptual reasoning in quantum mechanics. So this was a paper advocating for that approach when you want to teach teachers how to teach quantum mechanics. Next up was a numerical project. This was a project that was done with Livia Gutierrez and Marko Petrovic. And this is a really nice project where we had to combine both computational methods that involved working with numerics along with perturbation theory to properly handle the infinite time limits of the time evolution in order to get accurate results. And it's a really nice way of putting these two ideas together. This was part of a summer project. We call it an REU, Research Experience for Undergraduates, and I've been engaged in that with a number of people over the years. And many of these projects that I work on are related to quantum mechanics. This was another REU project. We found a general way of calculating wave functions algebraically using a generalization of the Rodrigues formula to operators. And I found this to be a really nice way of doing it. Previously, the only way I could figure out how to do wave functions often involved doing series expansions, and series expansions are just really painful to get involved with. So this was a project that was led by Joseph Noonan. Maz-ur-Rehman Shah was a person who had contacted me through the MOOC worlds, and he wanted to get involved in research. And I often pair undergraduates with a graduate student, so Logan Zhu was involved in helping out with this work as well. This is a paper that I think is a really cool new way of thinking about how you can calculate wave functions using operator manipulations. And I'm finding now that the methods that we developed in this really go much farther into helping us understand things like the relationship between classical mechanics and quantum mechanics, and also technical questions like, under what situations can I find raising operators that raise the energy of a quantum mechanical system? And these are actually projects that I'm currently working on. We don't have the publications for those yet. Then next up, I found another REU student, Anna Mazar, to help us with working out the single-shot factorization approach for bound states. Jeremy Canfield entered as the graduate student who was helping us on this problem. And it turns out that this approach that we had naturally takes us into a problem that was solved in the 1960s and 1970s by a Russian named Natanzon, where he figured out all of the different potentials that can be solved by hypergeometric differential equations and confluent hypergeometric differential equations, where you can get an exact analytic solution. But most of the potentials don't have an analytic formula for them. They're defined in terms of some set of complex equations that determine the potentials. And we showed how that fits together with this single-shot factorization approach, which involves writing the Hamiltonian in a factorized form. It's a very nice paper, has nice ideas. It doesn't fit it all into the book because it's chock full of calculus here and calculus there and calculus everywhere, but it was a very nice project. And again, we were able to honor Wes. Wes had done about 70–80% of the work that needed to be done on this. He hadn't recognized the connection to Natanzon potentials, although we strongly suspected it was there during the time he had worked on it. But that became clear with the work that Anna had done. Then next up, I decided to take a look at Heisenberg's matrix mechanics. I had always been interested in how it works, and we had discovered that it has a lot of relevance even today. So we wrote a paper for a special issue of the American Journal of Physics. This is with Leanne Dowdy and also Jason Tran. Jason is a graduate student at Georgetown. And we explain how if you change the postulates you want to use in quantum mechanics and postulate the correspondence principle in the form of Heisenberg's matrices have to solve the classical equations of motion, then you actually can derive the canonical commutation relation, commutator of x with p is IH bar, in a completely rigorous derivation. Not the kind of motivation that we did in the book, but it's really a rigorous derivation of the commutation relation. And I find that organization to be a much better way of thinking about how you should think about the relationship between quantum mechanics and classical mechanics. Then with Leanne, we wrote a paper, again this is a conference proceedings, talking about how it's probably better to teach entanglement using a delayed choice two-slit experiment with polarizers, because there everything is local as opposed to doing it with non-locality. Now, this isn't exactly the way that I did it in the book, but we certainly talk about this in the book. But at the time that I was writing that part of the book, I was still focused on thinking about things in terms of the Einstein-Podolsky-Rosen experiment, as most everyone else does. But we do talk about this in the book, and I think it's a really nice way of thinking about how to do quantum mechanics and teach entanglement. Then we came up with a really interesting thing. This is not in the book at all, but I think it's super exciting and really interesting. When we were doing the matrix mechanics project, I went in and looked carefully at the textbook Elementare Quantenmechanik by Born and Jordan, which was written in 1930. And I found in that, when they were doing their derivation for the simple harmonic oscillator, a really interesting line where they described how they could decouple the classical equations of motion and how they were related to the raising and lowering operators for the simple harmonic oscillator. I had read the same pages probably 10 times before and hadn't made that connection. But once I made that connection, I asked the obvious question, does this work for other problems? Now, in Born and Jordan's textbook, they really only solved the harmonic oscillator this way. They didn't know how to solve the other problems, but I did. And so I investigated this, and lo and behold, there is this really deep relationship between raising and lowering operators, the Schrodinger operators for the factorization method, and the method that you use to decouple classical equations of motion. And in many respects, this might be a new way of thinking about what the correspondence principle is. And I think it's also going to lead to a new way of thinking about a classical quantum correspondence. This is sort of the first paper on this, and it is leading us down, I think, what will be a very interesting path. We have a second paper on this where we applied these methods to the Kepler problem and also the Coulomb problem for hydrogen. And the Kepler problem is really interesting because when you decouple the equations of motion in this fashion, you have a super simple way of getting the orbits of planets. Much, much easier than the standard way of doing it. And I'm frankly shocked again that in the sort of 400 years since we've known how to solve for orbits, no one else has figured out how to do it this way. At least I've not seen anyone who has figured out how to do it this way. And so I think it's a really interesting new development. And then it has on top of it a natural connection to quantum mechanics. It's really cool and really beautiful. And as I said, this is becoming part of our ongoing work. So now I'm going to just show you a couple more projects that are either finished and have been submitted, or they're going to be finished soon, just to show you how much work has really been generated by this project. So in addition to the simple harmonic oscillator and the Kepler/Coulomb problem, we also showed how the classical and quantum raising operators are related to each other for the three-dimensional isotropic oscillator. I've also taken the work that we did in the book, exactly the stuff that we did in the book on time evolution for magnetic resonance, but here including how you solve it for arbitrary spin, which was a problem in the book. We've written a paper that shows how you solve that problem. We have submitted a paper on how you solve for the wave functions of the Morse potential algebraically. We've done a treatment of the asymmetric top. This is something that appears in the book. And the asymmetric top, I've always was bothered by the way other people had covered it. They would describe things and then they would say things that this is obviously a scalar or this is obviously a vector operator, so this is its commutation relations. But they would never actually derive the commutation relations. And I always viewed that as a cop-out. If you really believe that that is true, you should be able to show it, not just say that it's obviously true. Be wary of anyone who says something is obviously true. It often means that they really don't know the details to show it, even though they know that it has to be true. So we actually worked out an interesting way by looking at average and relative variables to really clearly show how it's done, and we calculated every single commutator that is needed to show that it really works. Then we have a paper that we're currently working on that shows why in physics classes we should teach row vibrational spectroscopy. It's a really wonderful problem, and when you work with it with operators, you can use the operators to get selection rules and other things like that. It's a really nice way of applying the quantum mechanics that you learn into experimental systems and being able to analyze experimental results by using the theory that's already been developed. And then a final project that I'm working on, well, actually, I think I have maybe another half dozen beyond this that I'm also working on, but a final project I'm going to list here that I'm working on, at least I think it's the final project, is algebraic calculation of wave functions for relativistic hydrogen. In the book, we did the 1s, 2s, and 2p, but I would like to work it out for the general case, and I'm working on this with both a citizen scientist and an undergraduate at Georgetown. Oh, there is one more. This is work that I'm doing with a high school student, the same person who did the time evolution for magnetic resonance. We also have an interesting paper we're working on now on the time evolution of the driven harmonic oscillator. And as a sequel to the work that we did in comparing classical to quantum mechanics for the simple harmonic oscillator, we looked in the classical mechanics, we looked at the damped harmonic oscillator, but we didn't look at that in the quantum mechanical treatment. The quantum mechanical treatment is a little bit more complicated. You have to use something called a Lindblad equation, which is even an approximate treatment because it assumes a Markovian process as opposed to a process that has memory of what has happened before. But we have actually now figured out how to work on the driven damped harmonic oscillator, and so that's going to be a project that we're going to be working on as well. And then the final one, now it really is the final one. I had mentioned this before. This work is sort of culminating in answering the question as to why, in general, you cannot find energy raising and lowering operators, even though you can for all exactly solvable problems. And it's kind of an interesting conundrum. But by working with the operators, we actually have a very clear and simple way of understanding why the general case does not work. So I've always said, sometimes just to myself, but often to others who will listen, that you really shouldn't write a book if it's not based on new research. With over 30 finished or in progress papers, I hope I've convinced you that this book that I've recently completed certainly satisfies that rule. And it's really been a lot of fun to get involved in something that is so rich and has so much new work and new things that can be done in a field that I think many people, if you ask them, they would tell you it's kind of a dead field. There's nothing new that you can do about it. But indeed, there actually is a lot of new things that you can do with it. And it doesn't just touch on instruction. Many of these new ideas are actually very valuable in applying to different kinds of research problems as well. And I have found that in a lot of the other research that I do, that these ideas enter into these other projects and really help us figure out things that we wouldn't have been able to do without having gone through this. So it's really been a wonderful experience for me, and even though this is a very long video, I hope you've enjoyed taking that journey with me to look through all of these as well. If we do a count, the work that I showed you includes 5 citizen scientists, 3 high school students, and 10 undergraduates. That's a pretty good record for a theorist in terms of trying to spread research projects out as broadly as possible. And I hope it also convinces you that really anyone can do this. You just have to develop the right tools and have the right thinking and mindset and the willingness to work hard, and you can do research as well. All of them were trained with the materials from the book. Hey guys, let's do quantum right.